In this video, I will give an introduction to the derivative. Specifically, I want to focus on two aspects of the derivative. Derivative as an instantaneous rate of change, and derivative as a slope of a line tangent to a curve at a particular point. As we'll see, these are really two aspects of the same thing though, approached from different directions. First, to understand derivative as an instantaneous rate of change, we need to know what an average rate of change is. An average rate of change measures, on average, how fast a quantity has changed over a period of time. For example, if I start with no money in the bank and 10 days later I have $100, then the balance in my bank account has increased by an average of $10 a day. Did I actually put in $10 each day, or did I put the money in all at once on a particular day? The average doesn't tell us that. It simply says that, on average, the balance increased by $10 a day. An instantaneous rate of change, however, measures how fast a quantity is changing at an instant in time. And we're going to see that an instantaneous rate of change is nothing more than an average rate of change where the elapsed time is minimized until it is essentially zero, but not zero. And more on this later. Second, to understand derivative as a slope of a tangent line, we first have to know what a secant line is and how to calculate the slope of a secant line. Now you may recall from geometry that a secant line is a line that intersects a circle at 2 points on its circumference. A tangent line is a line that intersects a circle at exactly 1 point on its circumference. Now, we aren't going to be concerned with circles here so much, but we will apply the idea of a line intersecting 2 points on the graph of a function, which we'll continue to call a secant line, and a line intersecting exactly 1 point on a graph, which we'll continue to call a tangent line. More importantly, we want to consider the slopes of these lines. Now, you may recall from algebra that the slope of a line is rise over run, or change in y over change in x, or y2 minus y1 over x2 minus x1. With secant lines, this will be easy to calculate because we have 2 points. But we'll run into a problem with tangent lines because we'll be dealing with only 1 point. To address this, we're going to see that a tangent line can be viewed as a secant line where the 2 points are moving closer and closer together until they are essentially 1 point, but not 1 point. Again, more on this later. Now, let's begin with a few questions. How do we know how fast Tim Lincecum's pitch was traveling at the instant this picture was taken? Or how do we know how fast Usain Bolt was running at the moment pictured in the photograph here? Or how can we tell how fast General Lee, the Dukes of Hazzard's car, was flying through the air as it approached the building in this picture? It may seem like a silly question, but how do we know whether the ball, the runner, or the car were moving at all when these pictures were taken? To answer these questions, we need to establish a few principles from physics. How do we know something is moving? Quite simply, we can only know that an object is moving if it changes position. And how do we know how fast it was moving? Well, if the car traveled 100 feet in 5 seconds, we can only say that its average velocity over that period of time would be the ratio of distance traveled to elapsed time. In this case, 100 feet divided by 5 seconds, or 20 feet per second. What we need now is a scenario that will allow us to move from average velocity or average rate of change to instantaneous velocity or instantaneous rate of change. Fortunately, due to gravity, there's a phenomenon known as free fall. So we're going to simulate dropping a coin from the top of the Empire State Building 1,250 feet above the ground. Now, physicists tell us that if we assume certain environmental factors, the height of the coin can be found using the function h of t is equal to negative 16t squared plus 1250, where h is the coin's height above ground in feet, and t is the time in seconds after it's released. Now, what you see on the screen is a graph that will be used to simulate the fall of the coin straight down. Then a second graph that gives the height of the coin over time and forms a parabola. And third, a table of values. These will give us 3 different perspectives on the fall of the coin as it moves through the air second by second. At time t equals 0, the coin has just been released, and so it is exactly 1,250 feet above ground. At t equals 1 second, the function tells us that the coin will be at 1,234 feet above ground. Since we now have two data points, we can calculate the average velocity from 0 second to 1 second. And we'll do this by dividing the change in position, 1250 minus 1234, or 16 feet, by the change in time, 0 minus 1, or negative 1 seconds, for a ratio of negative 16 feet per second. Now, since velocity has direction as well as magnitude, the negative value simply tells us that the coin is moving downward. So don't let this confuse you. Also, we're subtracting down from time t equals 0 to t equals 1 instead of vice versa because this will make our explanations a little easier later on. I realize that as we move from 0 to 1, we're going up by 1 instead of down. And as a coin moves from a height of 1250 to 1234, it's actually going down by 16 instead of up. But either way, one of these numbers will be positive and one will be negative. So the ratio will be negative and the average velocity will come out exactly the same. So don't be worried about that either. What is significant here is that if we were to draw a straight line, or what we called a secant line earlier, through the points 0, 1250 and 1, 1234, the calculation for the slope of that line would be exactly the same calculation for the average velocity between t equals 0 and t equals 1. And this brings us to the very important idea that the average rate of change of a quantity between 2 points in time is equivalent to the slope of the secant line connecting those points on a graph. Well, let's go on. At t equals 2, the object is now 1,186 feet above the ground, and the average velocity between t equals 1 and t equals 2, calculated the same way we did previously, would be negative 48 feet per second. And again, this is equal to the slope of the secant line passing through 1, 1234 and 2, 1186. It is vital at this point to see that the coin is moving faster as time goes on. The average velocity over the first second was negative 16 feet per second, but the average velocity over the next second was negative 48 feet per second. And since the motion of the coin as it falls through the air is smooth, the velocity of the coin must be changing constantly. And it raises the question, how fast is the coin moving at a particular point in time? Let's say at exactly t equals 3 seconds. Well, we'll move quickly through the rest of the data and come back to this question after the coin hits the ground. At t equals 3, the height is 1106, and the average velocity from t equals 2 to t equals 3 is negative 80 feet per second. From t equals 3 to t equals 4, it would be negative 112 feet per second. And again, this is the same as the slope of the secant line connecting those points. Between t equals 4 and 5, the average velocity is negative 144 feet per second. Between t equals 5 and 6, it is negative 176 feet per second. Then between t equals 6 and 7, the average velocity would be negative 208 feet per second, always changing, always speeding up as it continues to fall. Now you can see this in the simulation graph because the coin is falling a greater distance for each constant 1 second change in time. Between t equals 7 and 8 seconds, the average velocity is negative 240 feet per second, and at around 8.84 seconds, the coin will finally hit the ground. Now, let's get back to our burning question. How fast was the coin moving at exactly 3 seconds? Well, let's look at it this way. If the slope of the secant line gave us the average rate of change, then the equivalent to the instantaneous rate of change would be the slope of the tangent line, as pictured here. The problem, as I mentioned earlier, is that the calculation of a slope requires 2 points, and here we only have 1. And that would give us something that looks like 0 over 0, which at best is undefined and gives us no meaningful information to answer our ultimate question. So I return to something I said at the beginning. We can view an instantaneous rate of change as an average rate of change over smaller and smaller periods of time. We can also view the slope of a tangent line as the slope of a secant line, where the points are moving closer and closer together. So let's see how that works. We're going to use the same calculation, keeping the second point, t equals 3 and h of 3, constant, and moving the first data point, a variable data point, t comma h of t, starting from t equals 2, moving closer and closer to t equals 3, recalculating the height of the variable point each time, and then recalculating the ratio of distance traveled over elapsed time for smaller and smaller changes in time. So first you should notice that when the variable point is 2, 1186, the average velocity between t equals 2 and t equals 3 is exactly the same as we calculated previously and is shown above. Next, we'll jump ahead to t equals 2.9, where there is 1/10 of a second in the elapsed time between the data points. And then on to 2.99, where there's 100th of a second in elapsed time, to 2.999 and 2.9999, where there is only 1/10,000th of a second in elapsed time between the 2 points. Now, even though the difference in time may seem imperceptible, the ratio of the change in position to elapsed time is very meaningful, and it's getting closer and closer to -96 as the change in time gets ever smaller. By the time we get to 2.999999 seconds, or 1/1,000,000th of a second difference in time, the average velocity, it isn't exactly -96 feet per second, but the calculator can't tell the difference between the actual value and -96. So from this point, no matter how many more nines we add on to the end of the changing time value, we'll only get closer and closer to -96 without ever hitting it and without ever passing it. So that's what we call an instantaneous velocity, or the instantaneous rate of change of this function at t equals 3 seconds. It's also the slope of the tangent line, which would have the same value, -96 feet per second. Now, amazingly, this process of taking the ratio of change in distance over change in time with smaller and smaller time changes works out perfectly mathematically as well. But it involves a construct known as a limit. And this is something we'll cover in more depth shortly, so we can only discuss it briefly here in an introductory way. How does the math work? Well, remember that we're trying to get to a value of -96 feet per second. What we want to do is work through the same process we did a minute ago, but not have to make all those intermediate calculations. Basically, we want to find the average velocity as the time between the variable point and the fixed point becomes infinitesimally small. Basically zero, but not zero. Get it? Here's what it looks like. We have our formula, which is essentially the slope of a line between the variable point and the fixed point. Now, we want to evaluate this ratio as the value of the independent variable, t, approaches 3, but doesn't become 3. Because if it did, the denominator would be 0 and the value would be undefined. Now, watch what happens as we substitute the actual function for h of t and 1106 for h of 3, and then simplify. When we factor the numerator and cancel factors with the denominator, we end up with -16 times the quantity t plus 3. Since we want t to get closer and closer to 3, we can now just set it equal to 3 because there's no more denominator and we don't have to worry about the denominator becoming 0 anymore. When we simplify, we get exactly -96 feet per second. So this limiting process accomplished what we did previously by many calculations, and what we end up with is an instantaneous rate of change, or the slope of a tangent line. And this is what we call a derivative. So I hope you found this video helpful. If you have any questions or suggestions, or if I made any mistakes, let me know, and I'll do my best to address them in future versions of the video. Remember that you can always go back and pause, rewind, replay any sections that you need to see again. Thank you for watching.